Hello, class. I am back to recording lectures, and I know that you don't even know that I've been gone anywhere because you saw lecture 42 and now you're seeing lecture 43, which is really a continuation of lecture 42, but it's been a couple weeks. I've had to deal with some family issues and my father getting older, and I haven't really been able to get back to this for a little while, but that's why I preloaded the semester with a lot of lectures when I had time that I could do it. I want to recap the last lecture that we had, and that was on microstrip transmission lines. And what I've done is I've put down some things here from our last lecture so that you don't have to refer back to the lecture or even your notes. What we want to do now when we're talking about this, and I made an assumption. I said at the time that we really, for microstrip transmission lines that are working over the distance of your phone's printed circuit board are obviously very short, right? Very short. And we know that we can use the lossless line approximation when we've got very short connections or when we've got very low frequencies. Now, in a cell phone, we don't have the low frequencies. We actually have pretty high frequencies, but we do have those short distances, and that's why we can really say that we could discount R prime. And even though we've got R prime here seems relatively large, 0.162 ohms per meter. I mean, think if you went 1,000 meters. If I went 1,000 meters, that would be 162 ohms. There's not a, I mean, that would be a huge decibel attenuation, wouldn't it? And that's what we may find here. But since we're only going across the surface of the printed circuit board in your phone, those short distances, it really doesn't matter what it is. Because as long as it can conduct it, it should be fine over those very, very short distances. So that's what I've done here. We originally set it up as Z0 is 50 ohms. We had H, which is the thickness of the epoxy printed circuit board, and this is epoxy. And epoxy's relative permittivity is 4.5. We're putting a frequency of 1 megahertz through there. I'm going to compare this later to a frequency of 10 gigahertz, right, which would be 10,000 times as high. And you'll see that still the lossless approximation applies. We figured out that our, because we have a 50 ohm connection, we figured out that our ratio of the width of the printed circuit board trace and to the height of the thickness of the epoxy printed circuit board had to be 1.554. And we're still making the assumption, like we do in all undergraduate courses on electromagnetics and propagation theory, that G prime is pretty much 0. And you know, you could say that because epoxy is a great insulator, isn't it? As well as being a good dielectric, it's also a great insulator. So we really don't have any current flow from this top to the bottom, from the top positive surface, positive 16 volts, to the bottom ground plane on the printed circuit board, okay? And so we can, work with relatively high frequency stuff, and it's all going to work out because the impedance of the communication line is going to be all matched. Okay, so that's what we've got to work with, and what we wanted to find out is what is. I mean, if we actually put this whole equation together, not using the lossless line approximation, and by lossless line approximation, let me write that down again. The lossless line approximation that I'm referring to is that R prime would be equal to 0 ohms per meter, in addition to G prime being equal to 0 mhos, excuse me, per meter. Yes, I just realized that I have to get back into my lecture mode, which usually meant I had something to drink while I was lecturing. So this is the diagram that we've got, and that's a lossless line approximation. As you can see, we're not using that right here. So what we want to do is we want to actually figure out what the propagation constant is going to be. So our equation for the propagation constant, which I derived a long time ago, although you've only seen it a couple lectures ago, is R plus J omega L times G plus J omega C. And of course, those all have primes on them because we're talking per meter. And excuse me, if I say that G is going to be equal to 0, I can simplify that equation a little bit, and I can say that then that would be the square root. And I've done this, derived this for you before. I'm just going to write down what the formula is now rather than go through the whole derivation of it again. But it's the complex number that's minus omega squared LC, if we multiply that out, plus J omega RC, right? So you see that in the real part, I've got omega squared. So obviously the frequency is going to make a lot of difference in the attenuation constant, you know, as you would think. And then excuse me, I might have to get a drink of water. For the imaginary part, it's omega times RC. And of course that, we've got to take it to the square root. So these are going to be reversed in many ways, aren't they? But anyway, let's just figure out what the thing is first. We know what omega is. Omega is just 2 pi times the frequency. So I'll just write that down here. Omega equals 2 pi, or 6.28 times 10 to the 6 radians per second. So if and we've got L prime and C prime and R prime and everything up top here. So if we're using, now this is omega, remember, I'm just going to write this because I don't want you to get omega in your notes confused. And of course, so omega, you know, as 2 pi f. So in your notes, you can look at that. And of course, this is omega, but in the equations that we use to solve for L prime, W over H ratio, and the other things, we all used W. This is not a W, it's an omega, right? So we've got all those. So if we work that out and look at the actual propagation constant, what we get is that this is going to be the square root of minus 1.96 times 10 to the minus 3 plus J 143.5 times 10 to the minus 6. Okay? Now, if I take the square root of that, first of all, what I want to do is I want to write this not only in its A plus JB form, but let me write it in its, I mean, so you can check your notes if you're multiplying along with me. This would actually be 1.965 times 10 to the minus 3 at an angle of 175.8 degrees. Now that's its phasor form of the complex number that I've written out right here. I've just switched it into phasor form, and of course that means that the propagation constant, if I take the square root of that in its phasor form, is going to be 44.32 times 10 to the minus 3 at an angle of 87.9 degrees, right? And if I wanted to write that, the actual answer, in its complex number form, it would be 1.624 times 10 to the minus 3. I would hope that you would multiply these out yourself to make sure that you know, you're getting the exact same answers and doing it the same way that I'm doing it. I know you've got a lot going on, but You know, that would probably help. Anyway, plus J, 44.3 times 10 to the minus 3 radians per second. Okay. Excuse me, not per second, per meter. And of course, this is in nepers per meter. So I can change that to decibels per meter too, but it's really not going to be too much. I mean, if I wanted to write this in decibels per meter, and of course, let's remember that decibels are not really in engineering. It's like degrees and radians, right? We have to use radians all the time when we're working. We have to use nepers when we're working, you know, in mathematical equations like this. But if I was to change this into decibels via the 8.6, the minus 8.68 decibels per neper, then this would be minus 14.1 times 10 to the minus 3 decibels per meter plus J 44.3 times 10 to the minus 3 radians per meter. And I really even shouldn't write this as a complex number because it's not, right? This is the complex number up here, 1.624 times 10 to the minus 3 nepers and then radians per meter. That's what it should be. All I'm really doing here, in fact, why don't I just, I'm going to do this. Alpha equals this. And let's just box that in. So that's what alpha equals in decibels per meter. And then beta equals, just get rid of that, this. So there you go. There's your alpha and your beta, your attenuation constant and your phase shift constant per meter. But you've got to remember, inside your phone, how far is this trace really going? It's not going a meter. It's not even going probably 10 centimeters. So it's, you know, we don't really have to worry about this attenuation. I mean, let's say that I'm going 10 centimeters or 1/10 of a meter, then instead of being 14 milladecibels, it would be 1.4 milladecibels. I mean, there's no attenuation. Basically, what I'm saying is across the phone, there's such short distances, you don't ever have to do anything but look at lossless line approximations. And that's what we did here. If you remember when we used the characteristic impedance to find out what the W over H ratio was, okay? And so we've got that, and I think everybody can see that, yes, that's, we don't need it. Now let's do this again. I want to just block that off, and I want to look at the same, really the same problem. But instead of it being 1 megahertz communication across the inside of your phone, let's look at 10 gigahertz. Now, how much larger is 10 gigahertz than 1 megahertz, right? So 10 gigahertz is 10,000 times 1 megahertz. So 10,000 times 1 megahertz is going to give me 10 gigahertz. Now, here's another thing that I want to point out. 10,000, if I take the square root of 10,000, that equals 100. So what we really have to do is we have to take R sub s, because R sub s has the square root of frequency in it, doesn't it? So if R sub s has the square root of frequency in it, let's just look at the equation for R sub s. R sub s is the square root of pi times the frequency times the permeability of the conductor times the resistivity of the conductor inside a coaxial cable, or this. We'd really be talking about this conductor here and this conductor down here. The conductor for the ground plane, copper probably, and the conductor for the trace being copper as well. Okay, but here's what I want to point out is that it's got the frequency. So the square root of the difference in the frequency is just going to be 100. So really R sub s is just going to be 100 times what it is up here. So if R sub s up there was 251 times 10 to the minus 6, R sub s down here is just going to be 100 times that, or 251 times 10 to the minus 4 or 25.1 times 10 to the minus 3, right? So 0.0251 ohms, and then that would make our prime 100 times greater than we would have thought it be too. And of course, we know R prime is, so if I shift that over there, that would give us 16.2 ohms per meter, right? Wow, that's huge. That's 100 times as high as it is down here. 100 times as high. How's that going to change our equation then? Well, if you look at our equation, I've got minus the omega squared times L prime C prime. That's not going to change at all, is it? No, because that's the same thing that we had up there. So let's just look at this. This is going to still be the square root. However, something is going to change. And we're going to look at that too. So the first part of that's going to be exactly the same. Minus 1.96 times 10 to the minus 3, right? And, but the second part, plus J, now omega is going to be 10,000 times greater, isn't it? So instead of what we had before, where I had 143 times 10 to the minus 6, yeah, 10,000. Let me just yeah, that's just because R went up 100 fold too. Yeah, well, it's huge. Anyway, I get 22.84, which is, you know, a pretty large number. Hey, wait a second. Let me see if I've actually figured this out right. Just a second. Okay, I'm back again. Yes, I realized exactly what I did. That's not a minus 3, it's a plus 3, because it's omega squared. Of course, it's not going to be the same. This is 10 gigahertz squared as compared to 1 megahertz squared before. So that's crazy. Okay, yes, of course it's going to be different. So I get minus 1.96 times 10 to the positive 3, where that was minus 3 back there. And then over here, this is going to change from 1 megahertz up to 10 gigahertz, but then also R is going to increase, R prime is going to increase 100-fold as well. So this becomes 22.84, still small compared to what I've got here, the positive 3. So let me write this now as a phasor, right? So if I write that as a phasor, I end up getting 196,500 at an angle of 179.99, right? And if I take the square root of that, let's just go back here, I get, I don't have it in phasor form, but I do have it in A plus JB form, and that would be 0.0258 nepers per meter plus J 443 radians per meter. All right, so there we've got, I can also write this, that's alpha, and of course that's beta. This is alpha, and this is beta. And then if I also wanted to look at alpha for decibels, I would say that it's 0.22 decibels, or minus 0.22 decibels per meter. Again, you know, even at 10 gigahertz, we're still seeing that it's only minus 0.22 decibels per meter, and we're only going fractions of a meter. So, we're really not, we really don't have to worry about the attenuation constant when we're going over very short distances, like, the inside of a spacecraft or something. Very short distances, we don't have to worry about that. We still, look at beta, but of course, really, what is the manifestation of beta? It's really to lower the frequency, isn't it? So that's a loss of power due to an expansion of the waveform and a lowering of the frequency. That's the mechanism for energy loss due to, expansion of the waveform or lowering of the frequency. And isn't that what the energy is? Isn't energy of a waveform equal to Planck's constant times the frequency? And so if I lower the frequency, then the energy is going down, right? And that's what the phase shift constant really is doing. Okay, I'm going to finish up here for this because this sort of finishes this part of the course. And now we're going to start to go into a lecture looking at how waveforms change as they go down the thing, and look at standing waves and things like that. Okay. See you in the next lecture.